Dear friends, today we learn balancing of rotating masses in one plane. Let us consider mass m, which is turning at a constant angular speed omega at a radius r from the center. This mass will generate a centrifugal force in the radially outward direction, which is given by mr omega square. This centrifugal force is always balanced by a centripetal force. Let us try to see that how this is applicable in a real-time situation like impellers and fan. These components are named as or called as planar components. All these components will have some unbalanced masses, which I have shown in red color. These masses are really not seen in the industry, and but they have a centrifugal effect, and these unbalances mass are cause of vibration. So today we learn how to balance these masses. For simplicity, let us consider one disk which is turning at an angular speed omega. Let us consider that there is small amount of unbalanced mass mu which is at a radius r. Because of this unbalance, we generate a centrifugal force which is equal to mu into r into omega square. And these forces are shared by the bearings. Let us try to understand that the centrifugal force has a constant magnitude, and but the direction goes on changing as the system rotates from 0 to 360 degree. So balancing of masses involves redistribution of mass, which may be carried out by addition or removal of mass from various machine members. Let us say that there is an unbalanced mass over here, and if we want to balance, we have to provide an additional mass at a suitable radius just opposite to the unbalanced mass to balance it. So this is known as balancing by addition of mass. The other way is to remove this mass itself. So we can drill a hole and remove the material and remove this mass. These are the two methods of balancing. Let us say that we want to do a static balancing. So we understand what is static unbalance. The meaning of the word static unbalance is that the axis of rotation, which is shown by the blue colored in this figure, is eccentric to the center of gravity line. If you see the red colored line, which is a center of gravity, if there's an eccentricity between the center of gravity and the axis of rotation, we say that it is a static unbalance. The two lines have to be parallel. So static unbalance means balancing of several masses rotating in the same plane. So that is what is the meaning of static unbalance, given that all the masses are in the same plane. Let us try to understand how do we do the static balancing. Consider a mass mu which is at a distance r and is revolving at a rate omega radians per second. Now this will produce a centrifugal force which is equal to mu into r into omega square. Now if we have to balance, we have to provide a mass exactly at the opposite distance. So we can do it by resolving the components of mu r omega square. Let us say that mu into r into omega square cos omega t is the disturbing force in the horizontal direction. So that's a component in the horizontal direction, and there is a vertical component of the disturbing force which is given as mu into r into omega square sine omega t. If we provide a mass mb at some radius rb such that mb rb omega square becomes equal to mu into r omega square, then this mass would be balanced, and in that case the horizontal component of the balancing mass mb rb omega square cos omega t becomes equal to mu into r omega square cos omega t, and similarly the vertical component of this balancing mass mb rb omega square sin omega t becomes equal to mu into r omega square sin omega t. If this condition exists, then we say that the system is statically balanced, or this process is known as static balancing. And for static balancing, the condition is mb/rb is equal to mu into r. Omega square exists on both the sides, which has been cancelled. Now let us see the procedure of balancing the several masses revolving in the same plane using a single balancing mass. So till now we considered only one unbalanced mass, and we said that we could balance by providing one balancing mass on the other end. If there are more than one balancing mass, we have to use this procedure to balance all the masses by only one mass. So we can see, let us say that m1 is a mass which is at a radius r1 at 0 degree. Let m2 be a mass at a radius r2 at some angle theta 2, measured from the horizontal direction and in the anti-clockwise sense. Let us say that m3 is another mass at a radius r3 at an angle theta 3 from horizontal, measured in the anti-clockwise sense. m4 is another mass at radius r4 and at an angle of theta 4 from horizontal, measured in the anti-clockwise sense. Then m1 mass will produce m1 r1 omega square in horizontal direction. m2 r2 omega square will produce m2 r2 omega square is the force produced by mass m2 at an angle of theta 2. m3 will produce a force of m3 r3 omega square along its angle, and m4 will produce m4 r4 omega square along theta 4 angle. Now we have to balance it with one mass mb. So our aim is to find one mass mb at a radius rb at some angle theta b, such that all the four masses could be balanced. This will produce the force mb rb omega square. So this can be done by two methods. One is analytical method and graphical method. We will see both the methods one by one. So we start with the analytical method of balancing. In analytical method, we resolve all the forces into horizontal and vertical components. So let us try to understand how do we do that. So we show you the same figure. There are four masses which are unbalanced masses, and there is one mass with which we are going to balance. So what we do is that we resolve all the forces into horizontal and vertical components, starting with m1 r1 omega square. So m1 r1 omega square is anyway horizontal, so we start determining the horizontal components. m2 r2 omega square, we take a horizontal component for it. We take a horizontal component for m3 r3 omega square, take a horizontal component for m4 r4 omega square, and same way horizontal component for mb rb omega square. Next step would be to determine the vertical components. So we take vertical components of m2 r2 omega square, vertical component of m3 r3 omega square, and vertical component of m4 r4 omega square and mb rb omega square. Now we will sum up all the components separately horizontal and vertical components, and then try to equate and find the what is the value of mbrb and what is theta b. That is our interest. So with this, you can see the step 1, resolving the forces into horizontal and vertical components. Here we use sigma mi cos theta I, which is equal to m1 r1 cos theta 1 plus m2 r2 cos theta 2 plus m3 r3 cos theta 3, and so on up to mb rb cos theta b. The second step would be to determine the vertical components, which is given by sigma mi sin theta I, which is equal to m1 r1 sin theta 1, m2 r2 sin theta 2, m3 r3 sin theta 3, plus so on up to mb rb sin theta b. Now once we get this, we have to find the magnitude of mbrb. mbrb is given by square root of sigma miri cos theta I whole square plus sigma miri sin theta I. So with this we find mbrb. My next step would be to find the angle at which my mbrb vector exists. So that we do by sigma miri sin theta I upon sigma miri cos theta I. And then we take tan inverse to find theta. And to find the magnitude of the balancing mass required, we have to assume the radius, or usually radius is available with us. Now we go for the graphical method. In graphical method, we once again make this diagram. This is known as a space diagram. And then we try to make the vectors. So we make vector, the length of this vector is taken equal to mr. So for this vector it will be m1 r1, for this vector it will be m2 r2, for third vector it will be m3 r3, and then they are drawn at corresponding angles. So let us see that m1 r1 omega square is drawn at a horizontal, m2 r2 omega square is drawn at theta 2 angle referring from horizontal in the anti-clockwise sense, m3 r3 is taken at theta 3 angle, and similarly M4R4 is taken at theta 4, and finally we close the force polygon with MBRB. This force polygon, once it is closed, it shows that it is statically balanced. So this gives me MBRB omega square. So it gives me MBRB as well as it will give me the theta b angle. The angle of the vector will give me theta b angle. So what are the steps? Let's try to recollect all the steps in making in a graphical method. In graphical method, we are supposed to make the space diagram, and to make this space diagram, we require two things. We require mr for each mass and theta for each mass. So first step would be to find the product of the masses and the radius, individual m1 r1, m2 r2, m3 r3. The second step would be to find theta 1, theta 2, theta 3, which are the corresponding angle, and draw the vectors at that corresponding angles, considering first mass at 0 degree, and then we'll close the vector diagram by vector MBRB. The magnitude of the vector MBRB used to calculate the balanced mass MB at a suitable radius RB, and the angle of the vector represents the position of the balanced mass. So after making the space diagram, we have to simply make M1 R1 in the horizontal direction, as this M1 R1 is at the horizontal direction. Then M2 R2 at an angle theta B. So we'll remember that the next vector M2 R2 should start from the arrow of the previous vector, and the angle has to be taken from the horizontal direction in the anti-clockwise sense. Same way M3 R3, the next vector will begin from the arrow of the previous vector, and it has to be measured from horizontal and in the anti-clockwise sense. Similarly M4 R4, once again the angle has to be measured from the horizontal direction in the anti-clockwise sense, and at the end we close the vector, which will give me the length of this vector will give me MBRB, and the angle of this vector will give me the position or angle theta b at the position of the balancing mass. So this is the graph. Now we take one numerical and try to understand the entire philosophy of balancing, which is this is what is static balancing, the balancing when all the masses are in one plane. So let us read the problem. A shaft carries four masses 1, 2, 3 and 4, having mass 40 kg, 10 kg, 30 kg and 50 kg respectively, which revolves at radius of 0.6 meter, 0.5 meter, 0.3 meter and 0.6 meter respectively in the plane. The angle between 1 and 2 is 50 degree, and that between 1 and 3 is 200 degree. The angle between 3 and 4 is 60 degree. Find the magnitude and direction of the unbalanced force if the straight shaft rotates at 1500 rpm. Determine the magnitude and angular position of a balanced mass to be placed at 0.4 meter radius for static balancing of the system. So we'll solve this problem by both the methods, the analytical method and graphical method. So we will first step that we take to make a table. So this table will have 5 columns. The first column would be the mass number, second column would be the mass value in terms of kg, the third column would be the radius at which the mass is placed, the fourth column will be the product of mass into radius m into r, and the fifth column will be the angle of the vector. So mass number 1 is 40 kg and is at a radius of 0.6 meter. The MR will become 24. The angle is taken as 0 degree. Now the angle between 1 and 2 is 50 degree, and that between 1 and 3 is 200 degree. This is given in the data. So based on this, we have got mass 2 10 kg, radius 0.5 meter, MR becomes 5 and angle is 50 degree. Mass 3 30 kg, radius is 0.3, MR is 9 and angle is 200 degree. Now if we go for the fourth one, the data says that angle between 3 and 4 is 60 degree. Let us remember that we have to measure from the horizontal direction in the counterclockwise sense, and therefore mass number 4 will be having 50 kg mass, radius is 0.6, MR is 30, but angle is not 60 but it is 260 degree. And finally we are interested in what is in the mass MB. radius of balancing mass is given, so we add a fifth row where B is the mass, MB is not known to me, radius is known to me 0.4, MR is not known, and angle is not known. So our aim is to find the angle and the mass with the help of MBRB. So this is what we are going to do in this problem. So we'll start with the analytical problem first. So we start with space diagram. To make the space diagram, what we have to do is we have to make all the vectors one by one for each masses, and then we'll make a vector diagram. Sorry, we'll go by resolving the components. So let us have one m1r1 omega square at 0 degree. Then we have got m2 mass at radius r2 at theta 2 angle, which is 50 degree. So m2 r2. Then we have got m3 r3, which is at 200 degree, and we have got which will generate a force m3 r3 omega square. We have got a force, we have got a mass m4, which is at a radius r4 at angle theta 4, which will generate m4 r4 omega square. And our interest is to find mb at some radius rb, which we should generate mb rb omega square, and balance all the four masses together. This is what is our aim. So we'll try to find the horizontal component of m2 m1 r1 is anyway horizontal component of m2 r2, horizontal component of m3 r3, horizontal component of m4 r4, and horizontal component of mb rb. We will equate all this, and then we'll go for the vertical components. M1 r1 will have no vertical component, m2 r2 we get a vertical component, m3 r3 we have a vertical component, m4 r4 we have a vertical component, and mb rb also have a vertical component. Then we will equate the vertical components separately, and from this two we will find the mb rb and theta b. To do that, we have already learned that we have to find sigma miri cos theta I. So we start calculating m1 r1 cos theta 1, m2 r2 cos theta 2. We should remember that we have got m1, we have got r1, we have already calculated mr, theta is known to us. So all the terms in this element is known to us. Similarly, all the elements are known here. So we know each of these terms. So we can solve them, and at the end we are left over with mbrb cos theta b. So you get mbrb cos theta b plus 13.54 equal to 0, and therefore mbrb cos theta b is equal to minus 13.54. We will notice that this cos theta b term is negative. Then we go for the vertical components. Same way, m1 r1 sin theta 1, m2 r2 sin theta 2, m3 r3 sin theta 3, and so on, and we get mb rb sin theta b minus 28.79 equal to 0. Therefore mb rb sin theta b becomes equal to 28.79. We again notice that the sign is positive term. Now, as we have already seen, we will find mbrb. To find mbrb, we will take square root of miri cos theta I plus square of miri sin theta I. If we do that, we will find mbrb equal to 31.81 kg meter. For rb, which is given to be 0.4 meter, we get balance mass mb is equal to 79.5 kg. Now it is the turn to find the angle. To find angle, we have got the equation tan theta, which is equal to sigma miri sin theta I upon sigma miri cos theta I. From this we find theta b is equal to 64.81. But as the negative cos and positive sign indicates third quadrant, the correct answer will be 180 minus 64.81, which is 115.2 degree. So we have found the balancing mass mb and the angle theta b. Now we go for the analytical method. Sorry, graphical method. In graphical method, draw the space diagram. First step. Second step is to find m1 r1. We have already done. Then we'll draw the vectors m1 r1 m2 r2 at an angle theta 1 theta 2 theta 3. Then close the vector diagram and find the suitable mass mb at a suitable radius rb. So these are the steps. So we have reviewed the step solving the problem. So we take m1 r1 first and draw a line which is equal to length of line which represent m1 r1 to some scale. So in the vector diagram we make m1 r1 which is equal to 24. So some line which is of the length 24 at 0 degree angle. Then from the arrow of the previous vector, we draw one more vector. The tail of vector of the next vector joins with the arrow of the previous vector. The length of the vector is m2r2, which is 5, and angle is 50 degree from horizontal in the anti-clockwise sense. The third vector is m3r3. So m3r3 is at angle of 200 degrees. So we draw a line which is at an angle of 200 degree. The length of line will represent m3r3, which is equal to 9. And finally we draw a vector m4r4. Once again we should notice that we are measuring from horizontal line and in the anti-clockwise sense. And now we have to find MBRB. To find MBRB, we have to close the polygon. So we draw a closing line to find MBRB. The length of this vector will represent MBRB, and angle measured from horizontal in the anti-clockwise sense give me the angle. So you can see that angle is once again 115 degree and MBRB is 31.8 degree, 31.8. Now from this we can find the as RB is given, so we can find. So with this we have solved one simple problem in horizontal to find MB and RB by graphical and analytical method. I suggest all the students to solve this problem independently by yourself, and then if you have any questions you can email me, you can WhatsApp me, or you can call me at my numbers. If you have any doubts, please call me at any time. Thank you.